Hi, welcome back. This is section 3.6, which is on approximate linear relationships. So the reality of working in math in the real world is that nothing really follows a straight line all the time. We're approximating most of the stuff that we see. The math is very nice and clean with straight lines, but in reality, in practice, you rarely see a straight line come out of some data set. So that's what this section is on, is how to kind of just approximate what, an equation for what we see. So I've got a few data points here, whatever this data might represent. I think there's an example later on about crickets and chirping and things like that. So you can get all sorts of weird examples, but whatever's happening here, let's say, well, I don't know. I'm not going to make something up. Let's just talk about the math. If I want to graph these points, I can. And so if I just graph each one of them, I have a point at 3, 4, so I come to 1, 2, 3, maybe I should number these, 2, 3, 4, 1, 2, 3, 4, 5. I've got a point at 3, 4, so that's about here. I've got a point at 2 and 5, so that's about here. A point at 4, 1, so that's there. A point at 3.5, so halfway there, and at 2.5, so there. And then a point at 4.5. So somewhere over here and about right there-ish, right? So you can see that this kind of looks linear, right? We start up here and it goes down, whoop, kind of in a line, but it's not a straight line, right? It's not perfect. But this is a scatter plot, right? It's just a plot of a whole bunch of points. And so that's what we have to start with. Scatter plot is just a bunch of points plotted. They call them a scatter plot because sometimes it looks like it's just a huge scattering of points, right? But what we can do is throw a line that kind of represents this, right? It looks like, if I throw a line down there, it looks like those points kind of follow that line. In fact, a lot of them, the screen I'm looking at is like 2 inches big, but it looks like a lot of them actually touch it on the screen I'm looking at. This one touches it, excuse me, this one touches it. But the idea of this line is that it kind of goes through what we would call the middle of the points, or the average-ish area of these points. And there's a pretty complicated statistical formula to find this best line. And we're not going to go into that. We don't need to know that for this class. If you take stats class, you'll talk about it. When I say it's complicated, it's not really complicated. It's a pretty easy concept, but the more points you have, the more calculations you have to do to find this line, right? But we're not terribly interested in that detail of it. What we're really interested in is just being able to throw this line in the middle of these points. And this line is called there's a bunch of names for it. They call it the line of best fit, or the line of linear regression, or there's a third one I can't recall right now. Doesn't matter. These are what they're called, right? Oh, a trend line is also one. Trend line. Because it kind of shows that there's a trend. As my x-coordinate gets higher and higher, my y-coordinate clearly gets lower and lower, right? So let's look at another graph. I'm just going to throw a graph up here and we'll create a trend line for it. Right? If I have some points, and if I only have, say, these 4 points, it's not easy to say I can clearly see a trend, right? If I have these 4 points, well, yeah, it looks like there's probably a trend this way. But if I have more and more points, and all of a sudden, oh, wait a minute, I've got all these points over here, and maybe one down here, all of a sudden my trend line clearly changes, right? Instead of going through these points like this, the average looks like it's going this way, and these guys are just kind of, weird, not going with the flow type points. So with the points that I've got graphed here, my trend line would go kind of through the middle of them. Again, we're kind of eyeballing it. But there should be as many points on one side of it as there are on the other, and the distance from the line from each of these points from the top should kind of counter the distance from the ones on the bottom, right? Again, it's more complicated than that. We're not going to get into how complicated. It just should kind of look like this, right? Obviously, as x goes up, you're more likely for your y to go up than you are for it to go down, right? So, again, that's our trend line, and again, it should just kind of get through the middle, right? The middle, whatever you might want to call that, of this sets of graphs. Some graphs don't have a great trend line. Say I had this plot of points, I have no idea where that trend line would go, because I could literally justify throwing it anywhere, right? Because if I go this way, well, there's as many points on one side as there are on the other, the distance would be the same, I could throw through this way, I could throw it straight up, straight across. That's a terrible graph, right? It's a terrible, there's not a great trend here, right? And that's the idea behind the trend line, is to show if I increase my x, am I likely to go up or down with my y? Who knows? This is all over the place, right? So our trend line is only particularly helpful if I have a clear trend, right? If I have these points, well, then it's a bit more obvious. My trend line is probably somewhere like that, right? Now there's more points to the above the line than there are below the line, but the distance between these 2 points below the line kind of counteract all 4 of those points. So this would be a good guess for a trend line, right? All right. Let's look at this example. So down below, if you read down below, there's the starting with the trend line, or excuse me, starting with the example where 2 scientists, Margaret Brooks and Amos Dolbear, they counted the number of cricket chirps. And so they got this data. They went out and they actually took a lot of readings, a lot of data. They measured the temperature in the air, the humidity in the air, all sorts of things. And they counted the number of cricket chirps that they heard, and also the temperature, and they noticed in their data that there was a correlation between the two. So at one point they heard 18 chirps when there was 57, when it was 57 degrees, I'm assuming Fahrenheit, otherwise we're in trouble. 20 chirps when it was 60 degrees. 21 at 64. 23 at 65. 27, 30, 34, 39. At temperatures of 68, 71, 74, 77. All right, so they got this data. And the example graphs these. I'll try to do my best in graphing these. So I'm going to start here at like 15 and start here at like 50. All right. So on the x-axis I have chirps. simply because it was listed first. And then the y-axis is temperature, so this will be temp and chirps. Right? So I go up to about 80, so 50, 60, 70, and 80. And this is going to be pretty rough because I'm on a whiteboard. These go up to 40, so 15, 20, 25, 30, 35, and about 40. All right. So if I graph these, I've got a chirp, 18 chirps gives me 57, so 18, 57, 20 and 60, so 20 and 60, 21 and 64, 23 and 23, 65, 27 and 68, 30 and 71, oops, that's not right, 27 will be over here, and 68, 30 and 71, 34 and 74, 39 and 77. So, not a straight line, but I mean, not far, right? It's pretty straight. Right? I can throw a trend line into this. The trend line should just kind of look like it goes through the middle of these things, right? So it should just go kind of like, well, that's not a great one. I'm just nervous because I don't want to drag my red pen through a black dot. I hate that. Something to that effect, right? It looks like that line is a good representation of those points, that data, right? So that's my trend line. And in fact, it says down here, the two scientists of this example found that there's a relationship between the frequency of cricket chirps and the current temperature. And there's an equation. The equation of this line they came up with was the temperature as a function of the cricket chirps. Maybe I should do this as C. The temperature, which is a function of cricket chirps, right, was x plus 40, or C plus 40, right? Count the number of cricket chirps and add 40 to it, and that is your the temperature-ish, right? Of course, it's a plus or minus thing, right? Might be more, might be less, right? But it's a ballpark. And in fact, any outdoor enthusiast knows this temperature, scale. Sometimes they know it in centigrade. It's a different number, but if you're doing it in Celsius. But it's a good way of knowing the temperature. So if you're out there sleeping on a rock in the middle of Alaska and the temperature starts to fall, you can count those cricket chirps if there are any around there. However, this is good to kind of guess some points. So let's say you're out there in the wilderness and you hear 25 chirps per minute. Or it might be every 15 seconds. I don't know, I didn't read the example. I probably should have, but it's down below. But let's say you get 25 cricket chirps, right? Can you guess the temperature? Well, of course you can, because the temperature as a function of 25 cricket chirps is that 25 plus the 10, so it's about, plus the 40, sorry. So it's about 65 degrees Fahrenheit. Now we can see that that's true. If we had about 25, there it is, it would be about 65, right? It's pretty close to being accurate as far as these 2 points have suggested, right? Good. Now, what we've just done is called interpolation, right? Interpolation is an okay thing. It's using this data to make a guess for something within the data points, right? My data goes all the way down to 18 chirps, all the way up to 39 chirps, right? So anywhere between 18 and 39, I'm pretty okay to make a guess and say I'm probably going to follow this trend line, right? And that's opposed to extrapolation, which is not particularly okay. It's not always bad. Sometimes we have to extrapolate data and say, well, let's hope this trend continues, and if it does, this is what we get, right? But it's not always good, because if we say, well, let's hope this trend continues, then sometimes it doesn't, right? So for example, let's go out there and say, if I hear 200 chirps in this time period, what's going on? Well, the temperature as a function of 200 chirps is equal to that 200 plus 40, which is 240 degrees, right? So is it safe to say, well, when it's 240 degrees, I'm most likely going to hear 200 chirps? No, you're probably going to hear a cricket sizzling on the cement, right? So at some point, it gets too hot, these crickets go hide, they go run away, they die, whatever happens, this thing is not going to keep going forever. It's going to, once we hit around, you know, I don't know, 90 or some odd degrees, it is going to be like, nope, I'm out of here, no more cricket chirps, right? And so I can't really rely on this past that. I also can't rely on it going the other way, right? Can I come in and say, hey, I heard one cricket chirp, just the one, so I'm going to estimate my temperature. Well, that is 1 plus 40, so it's 41 degrees, right? Probably not, right? Probably not 41 degrees. That one cricket chirp, it was his last chirp as he's freezing to death, right? So we probably can't go very far out to either side and then consider this still a valid equation, right? We're kind of stuck between the data that we've seen, right? And so we can only interpolate this data. We can't assume that this line goes on forever. Okay. There's another example using, I'm not going to go through the whole example, you can read it down below, but I will talk about one of the things that it talks about with points that majorly skew this trend line. So the idea is that there's a class that all goes and gets tested for reading and IQ, but they've got IQ over here. They get their IQ tested, they get their reading level tested, right? And we end up getting a plot that looks like this. Right. As you might suspect. If your reading level is really good, your IQ is probably higher, and vice versa. If your IQ is higher, your reading level is probably higher, right? Not all the time, right? But this is the data that we got for one particular class, and by we I mean this example, I didn't really do this. But we have a higher IQs having higher reading levels, and that makes sense because we've got a trend line that kind of goes like this. I really don't want my red to get drugged through a black dot. It's the OCD in me. Then it's black and it drives me crazy. So I've got a trend line that looks like that going through this data, right? There was one kid absent that day though. This child comes in and they say, oh hey, let's go test you and redo this data. And this kid tests over here. He's got a really high IQ, but he can't read very well, right? And so what does that do to this trend line? I can no longer say that this trend line goes through this because now I've got this one point hanging out here. And if I try to compensate, my line has to do something. It has to turn somehow, right? And if it turns like this, then all of a sudden, it's not helpful, right? So this point out here, because it's so different from the rest, we call this an outlier. And again, there's a very specific formula to figure out if a point is an outlier. That's for later, that's for a 1040 class, or a stats class, right? But this is an outlier, and it's a point that doesn't really fit the data. A point that seriously skews the trend line. Right? It makes this trend line worthless to us, right? And so the interesting thing here is this, there is a scenario, I don't know if this is a real scenario or not, but in this scenario, this child here, it says, it's apparent that the new point has significantly altered the best fit line, blah, 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 some other stuff. In this case, the student in question was autistic and was particularly brilliant in math and science, enabling him to have a higher IQ, but was unable to read past a, I lost my place, but he can't read past whatever, a first grade level, something like that, right? So this student is in this class with all these other kids. He probably should be in a class of his own, or a class with other students like him. And that's what makes him statistically an outlier. We should probably be putting him in a class of other autistic students and seeing what their data is. And when we have an outlier, what we tend to do is then say, well, let's ignore statistically. This sounds so bad if you're talking about a human. This is a human life over here, but don't ignore the human, right? But statistically, God, whatever. Statistically, we're not going to count that data in this set, right? So it should be part of a different set. All right, I'm going to stop it here. Hopefully that was helpful, but I will see you guys next time for 3.7.